This example involves a linear combination of dependent normal random variables. Let's take a minute to read the problem. And as you see, this you have seen this problem before as a simple one variable problem in which y, the yield strength, was the only random variable and it was Weibull distributed. Here we consider it to be a three random variable problem in which we have introduced two more random variables, the dead load and the live load, D and L. And because we want to look at combinations of normal random variables, linear combinations, so we have made all of them normal. So yield strength is normal, the dead load is normal, and the live load is normal. And not only that, there is a little bit of dependence between D and L. So as before, we define the failure event as Q, the load, exceeding the strength A times Y. A is a constant, deterministic, and actually we need to find an appropriate value of A if the failure probability is not small enough. The first step would be to actually find out the statistics of Q, the combined load. The mean of Q is simply the sum of the means, as we have seen before several times, and the variance of Q now not only depends on the variance of D and L, but also on their covariance because they are correlated. So if you put in all the numbers, the variance of Q turns out to be 234.5 squared, the units being kip. Now the important realization is that Q, because it's a linear combination of normals, Q is also a normal random variable. Next, we define a new random variable which we call the safety margin. So the safety margin is AY, so strength minus the load, and if M is 0 or negative, we have failure. If M is positive, we have survival. So these are complementary events. M is also a random variable, as I said, so it has its own mean, which turns out to be 311.4 kip, and it has its own variance, which here Q and Y are independent, so there is no correlation term between them. So the variance is simply 370.4 squared. And just as Q was a normal random variable, M also is normal because it's the linear combination of two normals, Y and Q. So we have M as normal with mean mu M and variance sigma squared M. Now we are in a position to find the failure probability, simply defined as P of M less than or equal to 0, and we use the normal table to find that. So P of M less than or equal to 0 is the standard normal distribution function evaluated at minus 311 divided by 370, so approximately it comes to 20%. Now this is too high because our limit is 0.001. We discussed several options when we looked at this problem before, but here our preference is to increase the cross-sectional area A, and so that our failure probability is 0.001, or the argument of the normal CDF would be -3. And if we go through the algebra, we have one quadratic equation in terms of A, and if we solve this, the feasible solution is 84.3 square inch. So it goes up from 50.3 to roughly 84.3. So that would be the answer.